Hey everybody, welcome to another episode of Double E's Talk Tech. My name is Mike Hoffman.
And I'm Daniel Bogdanoff, and we're joined again by Stefan Loeffler, who's an optical guru, and we already, he made a grimace when I said that. He is, whether he wants to admit it or not, because you spent almost 20 years working with optical, off and on.
In the communications industry, yes, but I'm everything else than a guru. I'm just a marketing guy.
Don't sell yourself short. We're trying to impress the lovely listeners here, okay?
Don't listen to him. He actually is quite knowledgeable.
Yeah,
he was
check out
published by NASA. I was searching for something and I actually came across one of your NASA Tech Briefs articles from a year or two ago.
It was picked
cool.
up by NASA, yeah.
Yeah, that's pretty cool. So, we're back to space again. That was pretty quick. So, if you didn't see the first podcast we had with Stefan, you can check that one out. We'll put a link for that in the description of the video and in the podcast description if you're on a podcast engine. We talked kind of about the basics of optical, so Optical 101. And it came up at the end of that podcast that the expense of fiber optic links is actually getting them installed in physically on the earth or under the ocean or whatever it may be. So once those are installed, obviously bandwidth and data usage and requirements for people have gone up dramatically. So how do you optimize and do some clever finagling with your existing links to get more data across them? So the analogy I kind of think of is you have 6 people in a 5-seater car, so you just kind of shove people in the back seat and get where you need to go.
It's like hieroglyphs where you can say a whole sentence in one character, right?
Yeah, that's a great idea. Hieroglyphs.
So I imagine there's both communication tricks. So instead of it came up last time. Originally, it was just a binary 1 or 0 using light in general, but now you mentioned like phase multiplexing and all kinds of stuff. So that's one side of it is that instead of binary, you can now talk in higher
trinary,
ternary, yes, also possible.
But then there's more to it than that. So I don't.
Absolutely, yeah, and maybe we go a little by history, because the first race was between higher bitrates, that is basically more pulses per second, and more colors. So, and again, it was the erbium-doped fiber amplifier that made a decision somehow, because its capability to amplify multiple channels at different colors on the same physical medium.
Okay.
It made it unnecessary to split the channels into different receivers, then regenerate the signal and then send it out again. So you could just send the entire comb of wavelengths, as we call it, or the entire amount of colors through an amplifier. That was an early decision that, it's probably wiser to go with multiple channels at a moderate bit rate than with a single extreme high bitrate channel.
So do you mean 3 separate physical fibers, each one with a different wavelength of light?
It's different wavelengths on the same fiber, actually.
Okay, yeah, okay.
That's one of the nice things, as long as you stay in the linear area so that the signals don't influence each other. You can have multiple, actually up to 80 channels on the same fiber in the telecom window.
Well, that's just like a
color vocab. Sorry, go ahead.
Roy G. Biv. That just was a total light bulb moment for me. You said this is very similar to RF, and I'm just trying to figure out why. Will we do the same thing with, say, Wi-Fi, right? We have multiple channels that are all transmitting at the air at the same time, just at different carrier frequencies, and the receiver just filters the frequency of light it wants to see.
Absolutely, yeah.
Oh.
The colors are the equivalents to the carrier frequencies.
That's so obvious, but I just never... Well, obviously don't know anything. That's what we have you. I don't know anything about optical, but... Okay.
Yeah, so... And the fiber amplifier made the race, so it basically triggered a decision to go for this multicolor thing, as we call it. dense wavelength division multiplexing. Now, the other multiplexing principles are not ruled out. We do have space division multiplexing. First, of course.
Space again. Yeah. Okay. Sorry.
Well, it would be multiple fibers in that case. Or today we see experiments with multicore fibers, so or crystal fiber, where multiple transversal modes are transmitted in the same fiber.
You're going to have to say that again in
normal language.
Yeah.
Think of a waveguide in RF.
Okay.
And you're using multiple transmission modes. You're allowing multiple transversal modes to transmit different channels, so to say. That's also possible. It's still a pretty esoteric and academic thing. It's not made its way into commercial communication yet, but space division multiplexing is a possibility. So we have wavelength division multiplexing. Then there is polarization multiplexing. That's another nice property of optical fiber, that two waves at the same wavelength or frequency, or the same carrier, can coexist if they have different state of polarization. And of course, along the length of the fiber, they will change their state of polarization, their orientation, but their interrelationship remains.
Sure.
That remains constant. Right. Yeah, right. And in the end, at the receiver, you can demultiplex them again. So that's another possibility.
How many different polarization options, modes? Is modes the term? So
theoretically, you can have more than two, but practically it's two. Because then they're 90-degree interrelated, and that's easiest to separate out.
Okay,
it's actually the separation technology that decides how well that can be used.
Because we can transmit no problem, but the receiver side is the issue.
The receiver side is easier when it's just two.
But that basically doubles your bandwidth, right?
Yep.
On the same link.
So times two. Yeah.
So that'll buy us another year if Moore's law is a thing for optical.
Well, it's crazy to think. So for example, the transatlantic fiber, you were talking about dark fiber. So do you mean physically a piece of fiber that is not being used at all, or one of those 80 channels within a fiber core that have not been used yet, or both? Because you're talking about polarization and 80 lanes. That's a times 160 effect on a single fiber already. It's crazy.
Yeah. Well, dark fiber is actually a physical piece of fiber that's not yet been lit or put in for reserve, and then you decide to use it. That, of course, is the first step you do. If you have a cable with dark fiber, just use another dark fiber.
Sure.
Adding wavelengths is something that happens, and actually this time, as we speak. The so-called optical C-band in 1550, that's around 1525 to 1575 nanometers, was the first long-distance band that has been used, is now joined by the optical L-band that starts at 1575 and goes to 1625. So that's another 50 nanometers above, in wavelengths above, in frequency below.
When you say colors, I'm picturing different wavelengths.
Yes.
Is that accurate? So what's the difference between using different colors and using different wavelengths? Does that make sense?
Same.
So the word color isn't color in a traditional sense, not like it's the color of my shirt.
Yeah. Right. Okay. And since if we were in visual light, then it would be really colorful. If we try to visualize these systems, we often use different colors just because it's easier. In reality, it is near infrared, so it's 1550 is wide above everything we can see, but the equivalence of different colors still exists.
That would be such a cool visualization to be able to modulate.
Well, we should probably
inter-sea communications down into a.
We should probably interview a mosquito.
Are there some animals that can see infrared? It must be like a light show for them if a cable gets dug up.
Yeah, they can. Some of them can.
That's why they dig so often. Is what is this color coming from the ground?
So when we do this is total sidebar here because we're talking about something way cooler than this question. But when for example, my digital audio cable that connects to my TV emits a red light, is that just like a safety feature so I don't laser myself in the eye on accident, or because if it's transmitting infrared, then I couldn't see it at all, right?
And would you know? Would you feel it?
Oh yeah. So I guess would it even be a safety problem in the first place?
It could be. Yeah, it could be. transmission lasers that are used in telecommunication can have laser class 3B. That's possible.
So how many watts
that is,
or mil?
It depends on the wavelengths. There's a very complex rule. But you could say it's enough to burn a hole into your retina.
Okay. So that's a bad thing.
You get dark spots. Yeah, that's not good. Well, the fiber, the plastic fiber in audio equipment, it makes it just easier to handle. I mean, red light is something you can see. You know, there's a signal. If it's broken, there will be no signal. You can also see that. So all the testing, so to say, or the handling, knowing it's working or not working, is a lot easier with visual light. And but we were speaking about OTDRs before. And a good companion to an OTDR is a so-called visual light fault detector. And what it does is it sends red light with the same wavelengths you have. It's about around 630 nanometers into not so much the core of a fiber, but the cladding. And that travels along the fiber. And if you have a break, it will light up at this point because there is more reflection. So that's the visual fault locator is a great tool. If you have short distances, of course.
Especially if you have to go repair it instead of trying to measure it out.
Right, yeah. If it's in the connection panel or so, not in the manhole, of course. There you want to use this remote detection, but it's a great tool, yeah.
You don't want to dig up the wrong road.
No, yeah.
Yeah. Feels like it happens here more than
it does.
they'd like to admit.
So we were talking about extending the possible amount of data we can push through a fiber. So we've talked about essentially different wavelength channels within a spectrum on the fiber, polarization of the signal, providing an extra lane. Are there any other techniques?
The obvious one is, of course, to put more pulses per second. But there's, of course, a limit. You're broadening the spectrum of the signal, and that at some point competes with the neighbor channel that again has a different carrier. So it's like in RF also.
So to increase the baud rate or the communication rate, you have to have a wider signal, is what you're saying, or a wider
drive
band,
the modulation frequency, the broader it gets.
Okay.
Yeah.
Like a radio station here, you have a couple hundred kilohertz to play with before it start bleeding into the neighbor channel.
That makes sense. Because I'm just not going to go there. Cool. Okay, sorry to interrupt.
No, it's all good.
Yeah, and then the next step is coding. So you go away from just putting one bit in a pulse. You go into putting multiple bits in a symbol, and that's where, for example, PAM4 comes into play, where you allow more than two levels. In that case, it's 4 levels. A ternary signal that you mentioned before would have 3 signals. 3 levels: a -1, a 0, and a +1.
And are these intensity level or what?
That's intensity.
Okay,
it's amplitude modulation so far. You're pointing to it. It's the next is then using the phase modulation as well. And you start off with DPSK, QPSK, DQPSK, then go into QAM, and all of a sudden we have 6 bits per symbol.
So what is? Can you unpack some of those acronyms for us?
Yeah. Okay. Quadrature amplitude modulation, QAM, is basically what you use when you're using your satellite dish. The guys there have QAM signals, and they have also QPSK signals. Different coding methods that all rely on both amplitude and phase modulation.
Okay.
So you get those beautiful constellation diagrams from.
Yeah, that's what I was thinking.
Constellation diagrams are the new art form here.
I just can't believe that you're able to, because the difference in phase is 45 degrees? Is that, am I doing it right in my head? Or 23, is it 22.5 degrees difference between the phase for each of the states? Because 64 would be 8 by 8. Mm-hmm. Well, anyway, it's just very small differences in phase for something.
So
you were talking about
magnitude and phase, and that's your plot, and you try it. Okay.
But we're talking about terahertz of speed. It's unbelievable to me that we have that much accuracy to detect the difference in phase of something. You know, what would in time you're talking about probably billionths of a billionth of a billionth of a second. I don't know.
So
We're in the femtoseconds there.
yeah. That's also a word we don't. I guess we say.
A certain trick here is to allow some error, some failure rates. So forward error correction is a big thing, and
Forward error correction.
you put redundancy into the signal that allows you to calculate out or to compensate for transmission errors.
Okay.
And that's a huge part now. I mean, we're talking not about fractions of a percent. This is really several 10% of overhead. Yeah.
That's a lot.
Just to make an example, a QAM4 signal, 64 QAM with 64 gigabaud, that's 6 bits. Then, of course, we have times 2 for the polarization. That is intrinsic with QAM in optics, because we anyway do this phase and amplitude decorrelation or the demodulation. And as a result of that, we can also decrypt the second polarization direction. So it's always a factor of 2 in it. That gives us 768 gigabit per second, theoretically. But in reality, it's a 600 gig signal. So that's how much overhead is in there.
Wow.
In the form of noise and failures.
I'd like that
timing.
internet piped into my house, please.
Yeah, right. Where do I sign up for that? Do I write you a check, or how does this work?
Again, how do we sign up for it?
How do I get 600 gigabit?
You wanna
Think of
Ethernet
how
in my house?
many
you
simultaneous Netflix streams you could have going.
That's a problem, yeah. You would need a crowd of people to digest it.
I'm
And
sure
as
we'll
of
find
now,
a
you
way.
would also have to. I mean, your receiving equipment would cost you a fortune.
So 600 gigabit per second is about what the speed is for that transatlantic cable, or just cables in general, or
No,
what does that
this
number
is
represent?
the latest hero experiment. This was the buzzword on OFC last week.
Okay.
64. That's what everyone would cite, and it means 64 gigabaud QAM 64.
Okay.
And
So the difference, if I could step back a little bit, between QAM and PAM, I'm not sure I know
Yeah.
the difference there.
PAM is pulse amplitude modulation, so you just use the amplitude or the magnitude
Okay.
part of it. You don't look at the phase.
Okay.
PAM is QAM light.
So PAM is just up and down,
Right,
and
yeah.
QAM is going in circles, basically.
And of course, it has to do with how complex and how expensive the receiver is. So PAM is currently being used in shorter links,
Sure.
where you also get 100 gigabit per second per link. And if you want to go long distance, and if you have more money to spend, which means that the traffic going through it is simply more expensive, or you can charge more money for it, for managed bit. That's actually a term here, cost per managed bit and energy per managed bit.
Cost per managed bit, and okay, I'm just trying to, and energy per managed bit.
Then we're talking about coherent transmission.
So energy per managed bit, is that a managed bit, I assume, is a bit of data and not overhead?
Yes, yeah.
Okay. And then is there a energy consumption concern, or
Yes, absolutely.
like it takes a lot of power?
Yeah,
Or,
a considerable amount of this planet's energy consumption is meanwhile in communications equipment
interesting.
and data centers.
How much does a bit cost? Very open-ended question.
One
but-
Bitcoin.
I have,
But
too expensive.
I like it. I like it.
I have no good answer. Sorry,
That's okay.
fractions of a pence.
I'm sure it's pretty cheap, but
Yeah, it's more a scale. So the absolute
Sure.
number is not so important, but it's the scale and the
How you're doing.
comparability. Yeah.
Okay. Interesting. I never thought about power being. I understand data centers.
Yeah.
Power was a cost, and
That's
I guess
actually
that's communication.
power is a big factor in the race between copper and fiber. So copper is not dead. Let's make this clear. We still have a competition between copper and fiber, and the closer you get to the customer premises equipment, the more likely you will have copper.
Okay.
I would love to live in the U.S. with a fiber optic connection to my house. I don't get this at home.
I don't either. I'll be honest with you. Although this building, we have our data center here, and we have fiber piped in here, but a mile away where I live,
No.
they're like, nope, sorry. You get to use this company that starts
Maybe
with
soon.
C.
Maybe soon.
Google Fiber, Colorado Springs.
Please.
That'd be amazing. I would love that.
Well,
And Germany. Also Germany.
Yes, of course.
Colorado Springs and Germany.
Yeah, and give us free UHD television sets because we somehow want to make use of that fiber capacity. Yeah. Good. We spoke about the race between optics or between fiber and copper. If you try to bridge longer distances, you push more power, more electrical power into a copper connection than into a fiber connection. That's why fiber wins on long distance.
Okay. Does it win on data rate also? So the ability of it to communicate? Or it depends?
That race is not yet decided.
Okay.
So there is, if you look in the standardization community for 100 gigabit Ethernet, you find 100 gigabit Ethernet for short links on copper, and you find 100 gigabit Ethernet as LR4 on fiber. That's 4 different colors again, 4 different channels, wavelengths that get multiplexed together and demultiplexed again.
And that's because of energy consumption?
No,
Ish.
because
Oh,
of one thing is it's essentially the loss of the signal. So in order to compensate for the loss on the distance, you push more power in it, and that has to do with how much power you spend into transmitting, but also in decrypting.
Interesting. Okay. That makes sense. So fibers are obviously they attenuate the signal much less than a copper wire would.
Yes, the channel is uncritical. It gets interesting when you come to converting the optical signal back into electrical, then do all this decoding. You have to get the QAM signal into client-side signals. Probably, if we talk about 600 gigabit, I mean, how many channels is that? That is 600 1 gigabit channels. That will be a big rack of things. So you probably go for 10 gigabit, then it's still 60. 60 cables is also quite substantial.
Sure. What's the break-even point? Is there a rough, at this range you could kind of go either way? Has that been worked out yet?
Yeah, it's I would say around a kilometer.
Okay.
Yeah,
I was picturing
and it depends on multiple
20
factors.
meters
So,
or something.
No, you can go farther than that.
Okay.
But remember how many tricks we put into VDSL vectoring and so on just to get 100 megabit per second over a longer distance. That's about 4 kilometers, I think.
Okay.
There is not a sharp transition between where the fiber wins and where the copper wins.
Okay.
There's multiple factors.
So one thing you were talking about is this 64 by 64 technology, and you called it the hero topic of OFC.
Yeah.
When do we see that being implemented, and what is what's the runway on that? How long will that technology work before we need to look at 128?
How long
by
does
128?
it normally take for people to change over like that?
That would be a good topic for our prediction at the end of the podcast.
Okay.
Because that's
We are
up in the
actually.
air.
That was perfect timing. It's like you could see the whiteboard that says how much time we have left.
It's hard. It's really hard to tell. I mean, I've spent a few years in that industry, and at the beginning we would talk about 1.5 years between the next iteration in bandwidth.
That's quick.
No, that
seems
in today's terms that is slow.
Interesting.
A fellow from another company told me last week, or this week actually, you do a blink of the eye and you miss a state.
It's because it's light, right?
Yeah.
Have to have your
Ferris
eyes open.
Bueller reference there. Don't blink, you might miss it.
Yeah, right. That's the point.
What speed are we at today then? What's the normal higher end? Is it 32 by 32, or is it just something totally different?
Everything that makes 100 gigabit. 100 gigabit is being deployed in the field. So 100 gigabit can be realized in LR4, that's for wavelengths times 25, or 28, including forward error correction, that's on the client side, On long distance, it would be actually still QPSK, so not even QAM.
So they use different schemes based on who's going between.
Then you go 200 gigabit per second, 400 gigabit per second, 600 gigabit per second. That's the iteration.
Okay.
And that's another observation. We used to go by 110. The telecom people would go, that's Ethernet. The telecom people would go 1, 2.5, 4, 10. So
kind of step up.
Yeah, the steps were smaller in history. If you look at OM1, 2, 4, and so on. And now the Ethernet people are also at odd numbers. They would, in the past, they would never have done such a crazy thing as 600 gigabit per second. 600. 6 is absolutely no number for somebody in datacom.
It just doesn't feel right. Yeah.
Yeah, it's
it's arbitrary.
Yeah, right.
Okay, interesting. All right. So maybe we'll talk a little bit about rolling out infrastructure stuff in a third episode at some point with Stefan. That seems like a pretty cool topic.
Would be fun
to me
yeah.
also.
Agreed.
Predictions, I think you kind of covered your prediction a little bit.
Yeah, how long will it take until 600 gigabit per second goes in the network? Would say maybe 2 years.
Okay.
I'm going to go with something a little less serious. The whole entire time we've been having this discussion about lasers, all I can think about
space lasers
is that and sharks with laser beams strapped to their friggin' heads.
Okay, laser sharks.
I want to see a laser shark transmission network across the ocean.
Oh yeah, if you could like get a receiver on their tails and get them all to swim in the right direction, you could have a whole. And you could come up with a really cool shark acronym.
I predict that Dr.
OSM,
Evil.
Optical Shark Modulation System. OSM.
Exactly. Dr. Evil is going to invest heavily in telecom here in the near future.
Sounds like a plan.
Give us sharks with laser beams.
I'm trying to come up with a prediction, and I'm at a loss here. I'm just, I don't know what to say.
What about like optical and consumer goods? We don't really see.
Yeah, I was thinking about like instead of copper wires for the short run, I think we do see some optical type stuff and like opto isolators. Someone was asking me about they were going to get a scope for their young child to play with, and they were wondering if they should get opto isolator couplers for their probes so that their kids don't bust their scope. I told them probably not, but yeah. So maybe Mike's going to get a double prediction in for me, so I guess I'll keep you around as co-host for another.
Appreciate that. Yeah, Daniel, I've been watching the outtakes from the Scope Month videos, and I feel like the cutout Daniels weren't really quite cutting it from a conversation standpoint.
They left something to be desired in terms of topical depth, and they seem to have no opinions on anything. Just whichever way the wind blows,
Yeah. See what you did there.
Okay, that's a good as time is any to end. So. Thank you for tuning in to Double E's Talk Tech. Make sure you subscribe to the Keysight Oscilloscopes YouTube channel, and where you can see a video version of this, and to the Double E's Talk Tech podcast in your favorite podcasting engine. Hopefully, I'm going to say that again. We're working on getting a website set up outside of the normal stuff. So a little business there. We will get there, I promise. And we're probably already there now, so you should check the link in the description, or just do a search in iTunes or Stitcher or whatever it may be. We'll be back the second and fourth Thursdays of every month, and I'm Daniel Bogdanoff, my co-host
Mike Hoffman
and Stefan Loeffler.
Awesome. Thank you. We'll see you next time.